Thank you. I think the mic is working. So I will just start. Yes. So good evening, everybody. Welcome. It's a real pleasure to be here. I'm Xiaowen from the Department of Engineering Science at the University of Oxford, where I'm also part of the Oxford Mann Institute for Quant Finance. My background is in signal processing and machine learning, as Slavi pointed out. So today I will be talking about a subject that lies at the intersection of the two, which is learning graphs from data. But in particular, I will be focusing on a signal processing perspective, for which I would need to introduce you to the fast-growing field of graph signal processing. So we will explain that shortly. So feel free to interrupt and ask questions, since it's quite a long talk. The first question that we would like to ask is, what is the problem of learning graphs from data, or in short, graph learning in this talk? Usually the problem is that we are given a set of observations on a number of variables, which are usually represented by a data matrix X over there. Each row of the matrix that corresponds to the variables, so we have n variables, and then each column corresponds to a sample, so we have m sample for each variable. Now, given some prior knowledge about the distribution or model of the data, we wish to learn or build a measure of relationships between these variables. So the relationships can take a number of different forms. For example, simple correlation or covariance between the variables. But more often we are interested in a graph topology or operator or something equivalent, in which we consider each variable as a vertex in a graph. And the goal is to infer the existence of edges, possibly also the weight of the edges, such that it captures pairwise relationships between the variables that we have. So in the context of this diagram, I will basically decide whether there is an edge between V1 and V2 by looking at the two corresponding rows, which are highlighted in the data matrix X. So why this problem is important? First, the graph that we learn usually capture a geometry, the actual geometry of the structure of the data, which is obviously important for the processing, analysis, and the visualization. Also, to learn a graph or to learn the relationships between entities, they benefit numerous application domains. We can think about a brain analysis, where we consider different regions of the brain as vertices, and the observations would, in this case, can be the fMRI recordings in these regions. So the relationship that we learned is going to be a functional connectivity between different regions of the brain, which will basically tell us how they function together under certain situations. In the example of social network analysis, you can think of people as vertices, and the data would be their behavior, for example, the history of individual activities. In this case, what we learn will be the kind of behavior similarity or influence between these different people. So the other thing that I want to mention is that after you learn such relationships, usually they can help us to predict future observations or behaviors of this agent, which is obviously interesting as well. So now the question is that how are we going to build or learn such a graph, or in general pairwise relationships? So here is the outline of today's talk, which will be briefly split into three main parts. In the first part, I will give a very partial literature review on existing approaches, mainly from statistical machine learning perspective. Then I will move on to a signal processing perspective, for which I will first give you a very brief introduction to this fast-growing field of graph signal processing, or GSP for short. And then the third part will be a few example approaches in this new area for the problem of graph learning. And finally, I will give some concluding remarks. Okay, so first, a literature review. So the problem of learning graphs from data is in general a yield-post problem, because there are many different ways of associating a graph topology with the data that you have. The simplest way that you can think of would be, for example, computing a sample correlation, or maybe designing a similarity function using, for example, like a Gaussian RBF kernel. Or the drawbacks of this kind of approach is that they are purely data-driven, therefore they are sensitive to noise and also the parameter selection. What we want instead is usually a meaningful data model that captures a kind of relationship between what we observe as the data matrix X and what we wish to learn as the graph topology, while a model of function f, which is over there. So obviously this is not a new problem, and there exist two main approaches in the literature that can be interpreted using such a data model. The first one will be statistical models. So in this case, f usually represents a distribution or joint distribution of the variables, which is determined by g. So if you're familiar with a probabilistic graphical model, that in general is this case. In this case, what we learned actually is a factorization of a joint probability distribution of the random variables that we are interested in. There is another approach, a type of approach, which is based on a physically motivated models. So in this case, this f usually represents a physical generative model on the graph G, for example, a diffusion process on the graphs or networks. So in this case, what we want to learn is, in fact, the generative process of the signals that we observed. The easy example can be information propagation in social media or epidemics among human contact network. So due to the time constraint, I will mainly talk about statistical models. And then, yeah, I think if you're interested in the second one, I can give you some points of references. This statistical model, one typical example would be learning probabilistic graphical models. There are mainly two types of graphical models. One would be undirected graphical models, which we usually call Markov random fields, MRF. We can also have a directed graphical models, which is also called the Bayesian networks. Sometimes we can also consider a third one, which is factor graph, but that's less of interest here. So we will be mainly focusing on undirected graphical models, in which case we don't have directionality on the edges. So the point of an MRF is basically that the graph topology captures a kind of conditional independent structure of the random variables the nodes represent. The Bayesian networks simply allow the direction of the edges, and then it enables a more complicated notion of a conditional independence. The undirected one, which we will be mainly focusing on today, is also closely related to the signal processing approaches that I will talk about later. A Markov random field is basically a collection of random variables that follows satisfies a Markov property. One property that is of particular interest is this pairwise Markov property. So it basically means that if two nodes in the graph do not have an edge between them, then the two random variables that they represent will be conditionally independent given the rest. So here is the illustration. This kind of model can generally be represented by a family of exponential distributions, which is written over there over a parameter matrix theta. So this Px theta is basically the joint distribution of all the random variables. It is clear that we see that if there is no edge between, for example, Vi and Vj in the graph, then there is no interaction term in the joint probability distribution. Therefore, they are conditionally independent. So there are two main types of Markov random field. If the state of the node, the variable, is continuous, then it's usually called the Gaussian Markov random field. If it's discrete, then it is called a discrete Markov random field. In the Gaussian case, we can simplify the distribution above into the one down there with a parameter matrix theta. In this case, you can see that this theta is also what we call the precision matrix or inverse covariance matrix of the multivariate Gaussian distribution. In both cases, what we wish to learn is basically this parameter matrix theta that captures this conditional independent structure of the random variables. And usually we will consider a sparse matrix theta for two reasons. The first, the interactions in real world are usually mostly local, so that means you probably only have friends sufficiently close to you but not too far away. Secondly, the number of variables in this matrix theta, as you can imagine, is n squared, where n is the number of nodes. So a sparse theta will make the computation more trackable. So in the Gaussian case, where we wish to infer the covariance matrix or inverse covariance or precision matrix, one of the first approaches is by Dempster from 1972. The idea is very simple, which is to sequentially pruning the smallest elements in a sample precision matrix. So what it means is that if we have let's say we have a ground truth precision matrix that we wish to infer, and then from that we generate our data matrix X. Now we can compute the sample covariance and invert it, and then this method basically just try to sequentially remove the smallest entries, the entries with smallest magnitude, and then try to recover the one on the left. So you can see that if we remove the weaker ones, like the blue ones, it becomes closer to the one on the left. So it's a very simple and intuitive approach, but it doesn't work very well if you don't have sufficient number of observations, because in that case, the sample covariance doesn't approximate the true one very well. A more serious problem is that if you have the number of samples which is smaller than the number of variables, then you cannot even invert the sample covariance. So you cannot apply this method. So the second one that I will mention is an approach in 2006 by Meinshausen and Buchmann, which is based on the observation that learning a graph is basically equivalent to learning the neighborhood of each node. So based on this observation, they consider the observation at one node as a kind of combination of the observations on the other nodes. So here is one example. We consider basically the first row of our data matrix X as a kind of linear combination of the other rows. And then they try to solve this problem using a classical lasso regression. So here you can see that the first term, which is basically a data fidelity term that can be interpreted as a local log likelihood of this parameter beta 1. And they add the L1 norm of this vector to enforce sparsity. So this approach works well and with certain theoretical guarantees. So what they do is that after they get the neighborhood of V1, say these two edges, they will iterate, they will repeat the same procedure for the other nodes, and in the end, the relationship between V1 and V2 will be determined by the maximum of beta 1,2 or beta 2,1. So one potential drawback of this approach is that because of the lasso formulation, it doesn't work very well if the data are not IID samples. The other thing that I want to quickly mention is that the variables do not have to take a continuous form here if they are discrete, in which case it's a discrete Markov random field. Then the same regression can be shown as a logistic regression problem for discrete variables, which is very similar, but for discrete random variables. That's the approach proposed by Ravi Kumar in 2010. Okay, so now the next one, the next main approach that I will talk about is that instead of per neighborhood learning, we basically estimate the sparse precision matrix all at once, based on the idea of maximum likelihood estimation. So this is what is called graphical lasso. So many of you might be familiar with this because it's a very popular method. What it does is basically try to maximize the likelihood of a precision matrix theta given the setting of a Gaussian Markov random field. So that's the likelihood. If you take the log likelihood function, you will have the first two terms in this objective, and then you add the third term, which again enforces sparsity. So the difference from this approach and the previous approach is that you notice that the optimization in the previous case is decoupled for each vertex, where this one is a coupled optimization, which usually gives better performance against noisy situations. So this log determinant program is usually quite expensive to solve, but there are also efficient methods being proposed to solve it in a fast way. One example is the approach by Xie in 2011, and people are still working on this because this is quite a well understood method. So you will probably notice that in the previous case, these classical approaches, they usually end up with a precision matrix or inverse covariance matrix, which have both positive and negative entries in the matrix. So a positive entry basically is interpreted as a negative partial correlation between the two random variables, which can be undesirable in certain situations. For example, in a social network, maybe we want edges to be non-negative because naturally we want to measure the similarity between two friends, for example, by the number of friends they have, common friends they have. So one natural question would be, can we learn graphs with non-negative edge weights? The answer is yes. So some people, because of the reason mentioned above, focus on the learning of a subclass of precision matrices, which is called the M matrices. So these are special type of matrices that are symmetric. They're positive definite with non-positive off-diagonal entries. So they basically satisfy the non-negative weights that we are interested in. And in fact, if you adopt this kind of precision matrices, they lead to what is called an attractive Gaussian Markov random field. So it's a subclass of GMIF. Now the key thing is that, as we will see very quickly, the so-called graph Laplacian matrix L, which I will introduce soon, also belongs to these M matrices. And moreover, it's basically equivalent to the graph topology. It's equivalent to the JCC matrix. Therefore, it makes sense for us to shift a bit and focus on learning the graph Laplacian as a specific instance of learning the precision matrices. And you will see this is also very similar setting to the signal processing approach that I will talk about later. Because of that reason, there are a number of approaches that are proposed to learn this precision matrix as graph Laplacian L. In particular, the approach in the middle is direct generalization of the classical graphical lasso. So in the graphical lasso, you have a term which is the log of the determinant of the matrix. You will see this graph Laplacian L is a singular matrix, therefore you cannot evaluate the determinant. What they do is to propose a regularized Laplacian matrix such that it becomes non-singular. Therefore, you can take you can follow the same objective basically. Another reason, or which is the main reason that I want to mention this, is because this is very common setting to what I'm going to talk about, which is graph signal processing. For that reason, after this field has been introduced around 2013, there are many approaches from this perspective that solve the same problem, which is the one that I'm going to talk about now. But for that, I will give a very brief introduction to this new field, because maybe it's less familiar to some of you here. But I will try to keep it at the conceptual level so you can get the main idea rather than the mathematical details. What is a graph signal, what we call? It's basically a normal signal in the Euclidean domain, so Rn, with whatever positive and negative entries. But it is not defined in the real line, but it is defined on the vertex set of a graph. So that means it's basically a function that gives one value to each vertex in the graph topology. If you combine the two things on the left, you will end up with a representation on the right, which is not a Euclidean representation anymore. The good thing about it is that it takes into account both the structure, the edges, and the data, which are the values at the vertices. So sounds a bit abstract. I can give you some example. Here is one particular graph signal where I basically construct, I consider different places, basically 10 meter by 10 meter grid cell in the central area of London as a vertex on my graph. So I have 9,000 vertices here. Basically, it's a grid graph. But I connect two nodes when the distance between them is smaller than something, a threshold. So I will end up with a graph shown on the left, down there. The signal that I consider on the vertices of the graph will be, in this case, the number of Flickr users who have taken photos in that particular place, because the photos are geo-tagged. So you can see that you have a signal on the left where the values of the signal certainly has something to do with the geographical proximity between the locations, because if the two locations are quite similar next to each other, I mean just 10 meters, then maybe both of them are good to take a snapshot of a landmark. So there is a kind of correlation there. Another example would be in a social network, for example, Twitter. In this case, we have a natural relationship between two users, which is a following and a being followed relationship. The signal that I consider in this case is basically approximation of their interest in Apple-related products, the number of tweets that they post that contain some certain hashtags. So if we believe that the network in Twitter partially represent a kind of social network relationship, then it's likely that if you are interested in certain things and I'm your friend, then maybe I'm likely to be interested in that as well. So you can see that in this case, also the signals have something to do with the topology of the network. And in both cases, because the signals are related to the topology, therefore, whenever we try to process the signal or apply machine learning techniques, we would hope to take into account this underlying graph topology. And that's basically the main point of this area. So the immediate problem, if you're familiar with signal processing, is that this is basically a non-Euclidean domain. Therefore, we don't have a notion of shift invariance, which is central in signal processing. We don't have the notion of frequency, which is, again, very important in, for example, Fourier analysis. So for this, we would need to generalize the classical operators to the graph domain that can work in the non-Euclidean domain. What is called a graph shift operator will basically give us a notion of shift invariance, and the so-called graph Laplacian will basically provide a notion of frequency, which is something that I'm going to talk about. So I mentioned the graph Laplacian matrix before. Let's say we have a graph on the top left of 8 vertices. So the adjacency matrix is a very simple matrix W over there. In this case, it's unweighted. So there is a 1 if two nodes are connected, and if they are not, then there is a 0. Next, we can define what is called the degree of the nodes. In this case, it will be the number of neighbors that I have. So it's a diagonal matrix D over there, and we put it along the diagonal, which gives us a diagonal matrix D. The Laplacian matrix is basically the difference between the two. So the one shown in the middle. It's clear to see that it is equivalent to the adjacency matrix W. Therefore, it is basically the graph itself. It has some nice properties. If we assume that our graph is undirected, then this Laplacian matrix will also be symmetric. The off-diagonal entries will be non-positive if we assume the weights of the edges are non-negative. And then the rows, they sum up to 0 by definition. And because of that, you can see that it is a singular matrix because it has eigenvalue 0, which I will talk about later. So at this point, you may wonder why we are interested in such an operator. So the short answer is that it's a standard stencil approximation of the Laplacian operator in the continuous domain. And this similarity basically provides a notion of frequency for the signals on a non-Euclidean domain. To see this more clearly, say now on top of the nodes of my graph, I have a signal which is a 8-dimensional vector, right, over there. So if you apply this Laplace operator, you will see that this is basically a difference operator, because I will basically get the sum of the difference between all the values of the two nodes on the two ends of an edge, and then weighted by the weight of the edge. You can, a more commonly used form is this one. It's a quadratic form of your signal f, which is called the Laplacian quadratic. What this does is basically to do something similar, but raise the difference to the second degree power. So it is natural to see that this F transpose LF gives us a kind of notion of smoothness of the signal. So by that I mean, if a signal is smooth, that basically means that whenever there is an edge between two nodes I and j, I hope the corresponding values fi and fj to be small. Therefore, if you minimize this F transpose LF, basically you will enforce the smoothness of the signal. On the top right, you see a very simple example. Say we have these long bars to be +1 and -1. The shorter bars will be 0.5 of magnitude. Then the graph on the left has this quadratic term of quantity 1, and on the right, you just flip the values on vertex 3 and 7, you get something much bigger. But intuitively, you can see that the signal on the left is much smoother than the signal on the right, on this particular topology, right? So, so this means that we are closer, we are one step closer to the understanding of frequency, because in the classical case of the Fourier transform, the frequency basically is captures the rate of change in your signal, let's say in 1D. And now here we already see a rate of change, something similar. You can say the signal on the left has a much lower rate of change compared to the one on the right. So to make it very concrete, remember that this matrix L has a certain property that I mentioned, which gives rise to a complete set of orthonormal eigenvectors. So let's take the eigenvalue decomposition, which will be shown over there. So the big chi is basically a eigenvector matrix, and then the lambda is an eigenvalue matrix. Usually we sort the eigenvalues increasingly, so that means lambda 0 is smaller than lambda 1, then lambda 2 to lambda n minus 1. There's a nice property from spectrum graph theory saying that if your graph is connected, meaning that any node can be connected to another node while edges, then you will only have one eigenvalue to be 0. If you have multiple components in your graph, then the number of components will be equal to the number of the 0 eigenvalues. But let's say the graph is connected. For simplicity, we have this formulation where you see the second eigenvalue will be strictly bigger than 0. So these eigenvectors, they are basically also vectors in Rn. So we can think of them as functions or signals on the graph, obviously. And here I basically plot some simple examples from the first one, the second one, and then the 51st. So you can see the first one is basically a constant signal. So that means all the values are the same. The second one, you will see a kind of fluctuation from the bottom left to top right, because it kind of has a smooth transition from negative values pointing down to the positive values pointing up. And when you go to the 51st, then basically you see this variation happening all the time in the graph. So I would say in this case, the first one is obviously much smoother than the one on the right. And in fact, you can, just as I told you, we can use this Laplacian quadratic term to quantify this level of smoothness. We can basically evaluate chi 0 transpose L chi 0 to the one on the right. And from here, you will see it is going from a smoother case to a non-smoother case, because that's basically the definition of the eigenvalues, because the eigenvalues are increasing. So this basically means that from the first eigenvector to the one down there, we move from a low frequency component to a high frequency component. And if you are familiar with signal processing, you will see that conceptually these eigenvectors, they are basically very similar to the complex exponentials in the classical case, which we use to define the Fourier transform. So for that reason, we can generalize the classical Fourier transform in the graph domain. This is very simple. You just take the inner product between your f and each eigenvectors. These eigenvectors, they are basically acting like a kind of complex exponentials, which are building blocks of the signals that help us to evaluate the level of different rates of change. So if we have a signal, say, that have Fourier coefficients shown on the right, we will know that it consists certain parts of the frequency. In this case, the frequencies are basically the eigenvalues. So once we have this notion, we will be able to compare this with classical Fourier transform. So the one over there is the classical definition of a continuous Fourier transform, in which case we just evaluate the inner product between my signal and the complex exponentials. What we usually do in signal processing is to transform the signal into the Fourier domain, the frequency domain. Then we apply something like a filter because we want to modify the signal. And then we basically use the inverse transform to go back. So the filter can be a low-pass filter, which means that I want to remove, for example, high-frequency noise in my signal. That's typical in the image denoising example. But it can also be other functions. So in the graph case, I can basically have something exactly the same because I have a Fourier transform now. So what I will do is basically to transform the signal using the graph Fourier transform. And then I will again apply the filtering operation, which can again be one of these filters. And it's basically a 1D filter applied to the eigenvalues. And then I will use the inverse transform to go back. If we rewrite this, we can rewrite it in a matrix form where basically this g hat lambda is the filtering function that we care about. You can think of it as a matrix where this 1D function sits on the diagonal. And then we arrive on the term on the right. And because of the property of the eigenvalue decomposition, this thing under the blue bar can be usually think of as a function of the matrix L by itself. And the important thing here is that because of this, we will basically be able to interpret any kind of filtering operation as one where we apply a kind of chosen function of L to the signal that we have. And you will see this later. Okay, so once we know these basic notions, we will be able to move to the approaches that I will talk about. The idea is very simple. We have a signal here, let's say 4 positive and 4 negative values. And then we wish to infer a graph, so the connectivity between the nodes. Now the question is that I may have multiple choices, which are highlighted by the dashed lines, for the same signal. So I can basically choose whatever connection that I would like to. Therefore, I need a criterion for such a choice. So obviously, again, such a choice depends on the model that we think about. The reason is that if you have different graph, it will basically lead to different properties of your signal. So if you choose the signal, the graph to be G1, basically that will lead to a smooth signal, as I just explained. But if you choose the other two graphs, the resulting signal will be less smooth. So the idea would be to try to choose the graphs such that we can enforce certain desirable properties of the signals that we care about. Why would we want to do that? There are some limitations, as I mentioned before, about classical approaches. The main thing would be For example, for classical statistical machine learning approaches, usually they impose what is like a global distribution of all the joint random variables. Therefore, if you want to focus on part of it, it becomes more difficult. On the other hand, the signal processing tools, such as frequency analysis and filtering, they provide another type of regularizer, if you like, that can help us to learn the graph, because by regularizing against certain priors, we can end up with signals of different types of characteristics. So I will basically give you several examples, but before that, one last slide about the setup. In the classical signal processing approach, we care about a single function called fcx, so that's a synthetic view, basically, where my signal x is represented as a linear combination of the columns of f. So in the graph case, I know that my signal is defined on a graph G. Therefore, I adapt my representation f to be a function of G, and then I will have this new model. So the forward problem would be if you know G, if you're given a graph and your signal x, what you can do is to apply Fourier transform to understand the property of the signal. So that's like the forward step. We can do that using a graph Fourier transform or Wavelet transform in a pure mathematical way, or we can train basically over complete representations, which we call dictionaries, to achieve the same objective. The backward step will be if we are given x, we would like to design a particular model f, and together with the assumption on this parameter c, we can infer the graph G. So this is basically the idea behind all these GSP-based approaches. Obviously, the key would be, again, the model that we choose, which is usually based on a function of a kind of graph matrices, so adjacency matrix or Laplacian matrices. And not only the f, you will see also the assumptions on this coefficient c will also determine the signal characteristic. I will try to give you a few examples. So the first one, again, will be global smoothness. In this case, I told you before that usually we are interested in learning a graph such that the resulting signals are smooth. So this is, we'll go quickly. This is basically also the criterion in a few previous approaches where people also minimize this quadratic, Laplacian quadratic, because that's also a measure of smoothness. So think about the signal as the one over there, which is by assuming the f that we care about to be the eigenvector matrix of the Laplacian L that we want to learn. And then if we also put a Gaussian assumption on the coefficient c, where we design the covariance matrix to be the eigenvalue matrix that we wish to recover, then using the model on the top right, we will see that this x basically follows a Gaussian Markov random field. So a simple maximum a posterior estimation on this latent variable c will basically lead to minimizing the Laplacian quadratic. So I will not go into the mathematical details, but in the end, you will arrive at an equation on the bottom that basically says that I want to find another observation y, which is similar to my x, but I also want this y to be smooth on a graph that I wish to learn. So one simple example in the vector case would be this is my x, and then I want to learn another y, which is approximation of x, and then I also want to make sure that this y is a smooth signal on the graph that I learned. So I will go back and forth. You will see here, I don't know the edges. Here, I learned edges, and then I also recover a kind of a denoised version of my observation x. So this is one typical example where you see that the learning basically enforces a signal property, which is a global smoothness. And then the second one that I will talk about, it's going beyond the simple global smoothness, but consider the signals to be an outcome of applying a general class of filtering operations. So these filtering operations can usually be interpreted as a diffusion on the graph. So I will give you some example. If we assume that we have an initial signal on the left, that's the initial stage. If I follow a heat diffusion, then basically I will get the observation on the top right. If I follow another type of diffusion using a different operator, then I will arrive at the observation at the bottom. So the idea would be, if our signals are the ones on the right that we assume to be the outcome of some diffusion process, can we basically recover that diffusion process, which is basically based on the graph? Again, it is possible with certain priors that you choose. So in this case, for heat diffusion, we basically choose the F to be a heat kernel, which is exponential that involves the Laplacian matrix L. In this case, the model on the right basically says that my signal X is the outcome of a diffusion after time tau in the definition. And now I can say, let's assume that the signal that I observed, which is the one on the left, is a combination of the outcome of different diffusion processes. So you can see in this case, it can be decomposed into 4 different other signals, each of which will be the outcome of a certain diffusion process that starts at one node of the graph and then evolves after a certain amount of time. So that will basically lead to an optimization problem down there, where basically I still have this fidelity term and another sparsity constraint to make sure that I have only a few number of these diffusion processes. This problem is difficult to solve, but it's still possible, so I will not talk about that in more detail. And then it can also be generalized to a general polynomial case, I mean to replace the exponential function to a general polynomial function. This one, I think I don't have time to talk about, so I will skip it. So the third one that I will briefly mention is that in the previous 2 cases, you will see that the learning is basically to get a symmetric graph matrices or operator, because usually we assume that the graphs are undirected. But in certain cases, we also want to have edges with directions, because they may be interpreted as a causal dependence between different nodes. That's basically the idea behind the third class of approaches, which basically follow the idea of causal dependence. In this model, usually we consider the signals to be some kind of causal outcomes of the previous observations at the previous timestamps that I will talk about later. So here is one example. Think about this F to be any kind of polynomial of our matrix, the adjacency matrix W, and then think about the coefficient C in this case to be the signal observation in the past timestamp. And then I may have my X to be basically a linear combination of the observations in the past. So in this case, the edges can have directionality, and in this case, I would be able to interpret such causal dependence. And this problem can also be solved using a typical optimization problem that I will not talk too much. Okay, so basically, this is a quick comparison between the approaches that I talked about. The only thing that I want to mention is that you see that given different signal models, different assumptions on your operator and the coefficients, you will basically arrive at different approaches, which can give us the graph operator or matrix that we are interested in. So that's basically the main idea behind these kind of GSP-based approaches, because they not only provide a new interpretation of the classical models. So for example, the graphical lasso can also be think of as promoting a global smoothness. The filtering-based approach obviously allow a kind of diffusion model built on the graph. Moreover, they offer a kind of design flexibility basically goes beyond a simple Gaussian statistical model or simple diffusion model, because by designing the characteristic of your signal, you can learn the graph accordingly. Here are some simple examples that I will talk about. I will go through them quickly. One type of approaches focus on image, because images are natural graph signals on a regular grid. So the one on the right. What we are interested in is to learn the weight of the edges in this case. So for certain purposes, for example, I want to learn a certain type of weights so that it allows a more efficient coding. Which means sparsity in the coding coefficients after you apply the transform. Another type of typical application would be brain signal analysis, where we want to recover functional connectivity between different brain regions by looking at the signals recorded on different parts of the brain. And then there are other approaches that can be applied to infer a graph that captures the temperature evolution or other scenarios. In this case, it's also directed. Okay, so I think I will conclude soon. There are basically many open directions that I want to point out because it's still quite a young area. Obviously, we should think about the input that we have. Previously, I always assumed the complete observations. But it's likely that you have partial observation or sequential observation, in which case you have to design an online algorithm. For the learning outcome, you may think about learning a directed graphs or time-varying or dynamic graphs. Or you may think about learning graphs with certain properties. For example, you want a certain type of eigenvalue decomposition, distribution. You may, instead of learning a topology or a JCC matrix, just something like an intermediate graph representation, for example, a node embedding, which is quite common in machine learning. You can also learn something like that is like a probabilistic structure rather than a deterministic structure. Obviously, there's still a lot of work to be done to find the better signal and graph models. The ones that I talked about, they follow certain type of manually defined rules. There are people who start to look at a new type of approach that try to learn this model rather than define them. So using a kind of neural nets idea to learn the graph. And obviously, we care about theoretical guarantees and also what is basically the objective of the whole process. Do we just want to learn a graph so that we can apply traditional machine learning techniques, such as community detection, or we want to integrate the inference framework with the subsequent data analysis, for example, this image coding example that I mentioned. So here, the last slide, if you're interested in some papers in this domain, the top one, the one on top left is a recent review that I wrote. The one on the right is another review recently published. And then if you want to know more about GSP in general, there is a nice review down there. And then for those who are interested in deep learning, there is an increasing amount of interest in applying classical deep learning techniques to non-Euclidean domain signals. In fact, last year, I think there is a talk about a graph convolutional network by Thomas Kipp. It basically follows the same idea. So if you're interested, you can check that out. If you want to play around with the tools, there are MATLAB and Python toolboxes about classical signal processing applications. And I want to thank these three people for being the co-author of the first paper that I wrote for the review. So with that, I thank you for your attention and happy to take any question.
Maybe one or two questions. I think everybody should get on mic, or maybe you can even shout louder.
Okay, I think this works. Yeah. Could you give some intuition for why taking eigenvalues and looking at frequencies in this way?
Could you just be a little bit louder? I couldn't hear clearly, sorry.
could you give some intuition for why frequency considerations make sense when you're not looking at a time-based process? In a situation where the Laplacian corresponds to kind of a Markov chain, I understand what's going on, but otherwise I'm not sure why frequency is helpful.
Okay, so I think the question is why this frequency representation is useful. Is that right? Yeah, so basically I think it's more like a typical signal processing consideration where we try to somehow transform a signal in a domain that's easier than the original domain. If you think about the classical denoising example, usually we remove this high frequency part of the signal to achieve this purpose. So you can think of that as, I think in some ways similar to any kind of transformation in the machine learning domain, where you apply an operator to get a feature representation, and then you try to do something in that domain, for example, classification or clustering. But I think the high-level idea is that by going to the frequency domain, you really care about what are the changes that are present in the signal, and moreover, where do these changes occur? Can you localize these changes? And if you can do that, then you can basically enable certain type of processing tasks of your signal, where if you think about the classical Gaussian Markov random field, then it becomes not so easy to go into the fine details of a part of the signal and then to achieve certain processing tasks. So I think it's a different philosophy, but very closely related to classical transformation that you have in any machine learning technique, I think.
Okay,
Yeah.
Thanks for the talk. One question about model validation, model checking. So if you are posed with a problem where you have thousands of nodes and you don't have any prior knowledge about the domain, as in the as in the street example, for example, you wouldn't know that. Is there any work on checking whether your graph makes sense, as in, for example, generating samples from it or something like that?
So I think the question is that is it possible to somehow validate the model that you propose so that you make sure that it makes sense, right? Mm-hmm. Yeah, I think for what I talked about here, the models that we choose are still kind of manually designed in certain ways that follow certain intuitions, because I put the assumption that my signal should follow this kind of behavior. Therefore, I apply this kind of inference framework. But it's possible that given real data, you are not sure which model is the best one. And in that case, obviously, if you apply different models to a signal, you will get different results. There should be, I don't know if there are many work in this signal processing domain, but it should be possible to kind of have a comparison between all these models that you get in the end. For example, the consistency between them, whether one will be sufficiently different from the rest. Because in the end, I think you can probably always find a very good model to fit your data, but that's only your training data, the one that you observe, and it's difficult to guarantee that any other new observations will follow the same model. But yeah, I think it's a pretty much open question in this case. Easy example would be just take two approaches that I talked about and apply them to the same signal. Maybe two intuitions both work, and then you will see maybe you get something not dramatically different, but you should be able to quantify the similarity. So, for example, by just looking at the distance of the graphs that you learned, and use that as a metric to try to determine whether they're meaningful or not. Yeah.
There's so many other questions. If possible,
okay.
I know that there are quite a few. I'm sure you can grab
yeah, sure, yeah.
in the break. And with that, I think we'll reconvene after 15 minutes. Let's thank Xiaowen again.
Thank you.